Welcome back to chemistry. Today is our last installment of the lessons in the states of matter unit. We've been talking mostly about gases for the last, two and a half weeks or so. Kind of choppy here and there because you had spring break and this break and that break. But in any case, we are finishing up today with lessons 15 and 16, squishing those together, talking about liquids and solids because we've sort of touched on it along the way already when we talked about chemical bonding and intermolecular forces, and that's really what we're revisiting today. If you take a look at your mastery map here, we have in lesson 15 talking primarily about liquids, strong intermolecular forces playing a big role here. So we'll have to blast from the past that information, those topics, and then introduce some new ideas, new principles, the idea of viscosity and how compressible liquids are. But our main goals are really to relate or understand how those intermolecular forces occur between molecules and how they influence the kinetic energy of the molecules in liquid samples. Also, we're going to relate the molecular mass to a substance's phase. Is something going to more likely be a liquid or a gas if it's small or big, for example? And then finally, list some unique properties of liquids. And to begin, we'll just revisit this table that we looked at in yesterday's lesson. That is just to look at the states of matter, solid, liquid, gas, how they exist in our physical world. Ice, liquid, water. So we have solid ice, liquid water, and then gaseous water vapor in the form of clouds and humidity and steam. How those molecules behave, you'll remember hopefully that we learned that solids are very, very rigid. They take on a definite volume and a definite shape because the molecules don't move nearly as fast. They don't move nearly as much in terms of the size of their movement. They just sort of wiggle there. They're constantly vibrating. In a liquid, however, they vibrate enough to break free just a little bit. They stay close. They're afraid to leave the pack too much, but they branch out enough so that they can hit the walls of the container and take the space of the container. But the volume doesn't necessarily fill, so we say the volume is fixed. And then finally, we have our dear old gases that we've been talking about. Those gas molecules, I like to refer to the gas as the wild child. It does not care about the confines or the rules. He just speeds up and he gets going. He hits the container walls. He hits the top, the bottom, all around. There's virtually no intermolecular forces really holding them together, and they're just kind of on their own whimsy. They do not have a definite shape. They take the shape of the container always, and they will exceed the container. So they don't just take the volume of the container, but they will also, if we take the lid off, escape the container. This has complete and total relevance to what we're talking about today, and that is something going to be a gas or a liquid, and how do we know? So phases can primarily really be determined by intermolecular forces. And I've kind of created this table here where we see each of those molecular configurations of a phase of matter, solid, liquid, or gas, and how they behave. And then also we can kind of think about how many intermolecular forces must there be in order to achieve this sort of configuration. Also, what's the kinetic energy? And then what's the relationship between intermolecular forces and kinetic energy to form that shape, if you will. So we'll start with solids. Take a look at solids here. Actually, we'll go across. We'll go solid, liquid, gas, so we can compare. Intermolecular forces, the amount of them. Here we're really talking how many are there and how strong are they. In a solid, there are many, and they're very, very strong. So here, a lot of times you think of intermolecular forces, we talked about dipole is our temporary ionizations at the ends of molecules. Linden dispersion are very, very temporary dipoles. Nanoseconds in length. We talked about dipole ions. So ions, excuse me, I'm doing this late at night. Ions have a strong attraction for another full ion because it's a full charge, not a temporary charge. So those are very strong. And I'm drawing a blank on the fourth right now. Hydrogen bonding. Oh, how do I forget about hydrogen bonding? Anyway, Solid ionic substances are held together. Basically, it's a type of bonding, but it's an intermolecular force as well. That positive negative attraction, the opposites attract. So there's a lot of intermolecular force going on here. Way more than we have in liquids. Liquids have some, you can see them clustered together where they form those kind of clicky things. But as I said, some of them they're loose enough to get out and travel. They do come back. So when we watched that animation yesterday, some molecules might jump out for a little while and take a walk somewhere or take a swim or whatever, and then they come back and rejoin the group. We say that the amount of intermolecular forces here are less than as in solids, but not quite as few that are in gases. So liquids are middle of the road when it comes to intermolecular forces. And then for a gas, we have very, very little intermolecular force. Really nothing is holding them together. Now, in the ideal situation, you remember there are no intermolecular forces, which isn't true. Of course, we have intermolecular forces. In fact, with HF, which is a gas, fluorine being the most electronegative atom, we have intermolecular forces and it's very, very, very strong hydrogen bonding, but they just don't matter as much as this next column we're going to discuss, and that is kinetic energy of those molecules. So in a solid compound, the molecules have very little kinetic energy, and we saw that the molecules just sort of vibrate there in their grid, in their cube, in whatever shape that they have formed. Whereas with liquids, as we turn up that temperature and our molecules start to move a little bit more, as soon as they break free a bit, they have more range of motion, right? They're not hitting other molecules around them, so they can move more, and they can move bigger, and they can move faster, and they do. This is wrong. I should have changed this. This should say there is more kinetic energy than solids in a liquid, but less than gases. So again, liquids middle of the road when it comes to kinetic energy. But gases have tons of kinetic energy because all they do is move. They're usually found at very high temperatures and or very high pressures. And so what we're really concerned with is the relationship here. If we look at a sample and can compare what's happening, we can determine the phase it's going to be or the phase that it is. So if we look at a situation where the intermolecular forces far outweigh the kinetic energy of the substances, we do have then a solid, because we don't have a lot of movement, but we don't have a lot of movement of molecules, but we do have strong attractions between the molecules. It's going to result in that solid structure. When we have intermolecular forces still weighing out, like still winning over movement, kinetic energy, we have a liquid. You'll notice there's one less greater than sign there, which basically means it's not quite as much. It might be slightly more. Intermolecular forces win out because they're tied together still to some degree, but they are also moving a little bit more than they were before. And then finally, when we have a situation where there's very few intermolecular forces compared to how fast those molecules are moving, we are looking at gases. So that's really the take home here. If you're looking for what's the message here, Mrs. Crosis, it is the combination, the consideration of both intermolecular forces between the molecules and the kinetic energy of the molecules that you have to look at when you're considering what phase might this take on. And that's your understanding piece. That's the conceptual piece that will help you look at a scenario and think through it. The remainder of what we have here in the properties of liquids lesson is really going to tell us about liquids and how they behave and some unique properties about those. So the very first thing we're going to talk about is the fact that molecular mass and shape have a lot to do with what phase a substance will take. We talked about chemical bonding. We did a whole mini unit on organic chemistry. And so I'm going to show you some molecules, and hopefully blast from the past, you will remember the types of molecules we were talking about there. And in this particular example, you can see that we're using all hydrocarbons. right? All carbon, all hydrogen molecules, and they range from 1 carbon all the way up to 10. So we start with methane, we go all the way to decane. When we have only 1 carbon, we have 4 hydrogens, but when we have 10, we have 22. The difference here is huge in terms of their molecular masses, because carbon alone is 12 approximately. So just from carbon alone, decane has a molecular mass of 120, whereas in methane it's 12. So we have increased its molecular mass probably by about 10 times to go from methane to decane. So decane is a much, much bigger molecule. It's much, much heavier. And it's long and it's branched out. So if you remember how we drew molecules, we drew them in a zigzag, and every carbon was a peak, right, or a point. So if we drew decane, it would go something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, versus methane, which is kind of small and compact like this, right? Carbon with 4 hydrogens. Big difference here in both mass and shape. So what we find is that heavy, long, floppy molecules tend to be liquids. Decane, you're almost definitely going to find naturally occurring at room temperature, at our room temperature, as a liquid. As is octane. That's what you fill your gas tank with. It, of course, comes out of the pump as a liquid. You can smell it. It's a very strong smell because it's very volatile. That means it has a low, relatively low boiling point. 126 degrees C. That's not too high. Most of it is a liquid at that temperature. Whereas methane is completely a gas at room temperature. A negative boiling point is going to give us a gas at room temperature. So you'll see methane, ethane, and propane all being gases at room temperature. And butane. Anything that's less than room temperature is about 25 degrees C. So those 4, and we really start getting to see our liquids when we start with pentane, 5 carbon chain. Okay, so larger molecules have greater masses. Greater masses result in London dispersion forces. So remember, London dispersion forces are those temporary dipoles where we might get a plus here and a minus here for in such a small second, and then they reform because those electrons just move around, and in those milliseconds where they have a conglomeration of electrons in one section, then they have a temporary dipole. In any case, when you have more atoms and you have more mass, you have more ability for this to happen, so that there would be more intermolecular forces between more IF between atoms of larger compounds. Sorry for my handwriting. Kind of not in the best configuration here. So that's our first piece. Longer, bigger molecules tend to be liquids when we're comparing. And I have to apologize. I had a whole bunch of examples in here, and my file didn't save the right way, and I didn't discover it until just now. So if you have specific questions on the quiz after your first attempt, please email me them. I will check and I will get back to you as best as I can about it. I just didn't have any more time to redo that part of the lesson. And so it goes with the rest of my lesson, unfortunately. Okay, so some properties of liquids. We might have heard of the word viscosity before, or a liquid is viscous. We're going to talk a little bit about vapor pressure, compressibility, and surface tension. You'll see some pictures that go along with this to describe each of these phenomena. We're going to define them and briefly just say what they are and how they come to. Again, I had a bunch of examples for these as well, and someday I will find the file. You know, I'm using that Microsoft OneDrive, and my computer has to upload it, and I don't know, it's getting all confused. It's somewhere, and I just can't access it right now, so I do apologize. Okay, viscosity. Viscosity has to do with the space between molecules allowing a liquid to flow. So if we go back and look what what the molecular structure or organization is of liquids, we see that we don't really have much space between the molecules and the atoms in a solid. However, we begin to see that empty space emerge when we have a liquid, and then of course we have huge amounts of empty space when we're looking at a gas. It's those empty spaces in the liquid that allow it to conform to the shape of the container and ultimately to flow out of the container. So when intermolecular forces are strong, for example, in water, they work against the natural inclination for liquid to flow. So they're not quite as strong in water as they are in something like what's pictured there, which is honey. I'm not sure what the molecular formula is for honey, but I'm sure there's lots and lots and lots of intermolecular forces holding them together. It basically makes the substance more rigid, right? When we were comparing here and we're looking at the amount of intermolecular force between molecules versus their speed or their movement, we're looking at the fact that more and more intermolecular force we have, the more rigid the molecule will be, even if it doesn't totally turn to solid. So think about Jell-O. When you make Jell-O, you mix the water with the powder and you put it in the fridge, and it starts as a flowable liquid, and you bring it out and it's like Jello, and it's all like sort of solid, but not really, because you could push your spoon through it and it jiggles, and if you let it there, it'll melt. So it's the empty space that allows it to form. And those intermolecular forces basically will restrict the ability for that flow to happen if they're holding so tight, because they're going to limit that amount of space. So the flowability, that's probably my own word, is referred to as the liquid's viscosity. Maple syrup, honey. I think the example I had used was I don't even remember. I think I gave you choices like antifreeze, which is kind of liquidy, gasoline, which is liquidy. I don't think it was a food. I can't remember. But when I asked my husband for help, he said suntan lotion. Suntan lotion's kind of viscous. It's kind of thick, especially if you get like the zinc oxide. It's not exactly a solid and it's not exactly a liquid. You can push it through a hole, but it takes some effort and it's kind of sticky and ooey gooey. Toothpaste. Toothpaste is a highly viscous liquid. The viscosity is directly proportional to the amount or type of intermolecular forces holding the substance together. So when you have something like honey, you have either a high degree of intermolecular forces, there are many of them, or you have intermolecular forces that are super duper 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 strong, or maybe you have all of the different types of intermolecular forces in one bunch of compound. Okay, moving on to vapor pressure. Vapor pressure has to do with the gas molecules of a substance sitting above the liquid molecules of a substance. So looking at vapor pressure here, we're showing boiling water on a stovetop. You don't have to boil the water in order to get some gas water molecules above the surface. In fact, this is happening all the time, even in my cup. Whoops, I have a glass of water, right? Can you see that? Yeah. There is a vapor pressure to this water. It's not 100 degrees C, and so we're not boiling it, but some of those water molecules, and I mean some, very few, are escaping, and they're not leaving too far because they do have some attraction to this water, but they're creating a vapor pressure because they're popping it out and they're popping back in, and they're popping out and they're popping back in. What happens is that it forms what we call an equilibrium. Okay, so some molecules get enough energy to break free. When they escape, they float around above and they exert a pressure back onto the liquid. It's kind of like a fighting. They're sort of torn. They left, but they didn't really want to leave, and so they're going to hang out there. What happens is naturally, the more gas molecules you have above that surface, the more pressure is going to be forcing down on the surface. So hotter liquid samples have higher vapor pressures. When you boil water, for instance, you have a higher vapor pressure. A hot tub would have a higher vapor pressure of water above it than a swimming pool. It doesn't have to boil. It just has to be warmer. Okay, we talk about compressibility. This picture comes from the course, and it has to do with your brakes in the car. And not so much the brakes themselves, because those are solids, but there's brake fluid in there that you need in order for the brake pads to push against your brakes and not grind, right? So the brake fluid provides some lubrication between the two. What happens when we're talking about compressibility is we said gases can compress. That's a fundamental property of them. Go back to lesson 2. It's one of the 5 properties we discussed early on. We can squeeze the volume down. That's compressing a gas. We cannot do that with liquids. So they are not really compressible because there's not sufficient space between them. Remember, we're just starting to emerge, or we're just starting to grow that space between molecules as we form, or as we phase change from a solid to a liquid. So there's not enough. If we start pushing them together, they're going to reform as the solid. And so we don't have that ability as easily to compress them. Instead, the molecules in a liquid transfer pressure. So this molecule over here feels pressure, and it'll just transfer that pressure energy to another molecule rather than squeeze in on it. Somehow that energy just gets moved, and it's sort of like a domino effect. It'll pass through, and the other side of the sample will feel the pressure and exert it onto the other object that it's touching, and that's why they work so wonderfully for our brakes. The last property we talk about here is surface tension. Surface tension we talked about in our hydrogen bonding lesson when we talked about intermolecular forces. Surface tension has to do with those liquid molecules of water or any substance that can hydrogen bond, like ammonium, what else? Maybe hydrogen disulfide. Those are gases though. It's tough to find a hydrogen bonding liquid, purely hydrogen bonding. I would have to think about it. Maybe acetone, some of the organic ones. In any case, liquid molecules are held together so strong by intermolecular forces that they're super duper strong or tight on the surface. And the molecules deep within it, they're tied together too, but just not as much as on the outside. Because the ones on the outside only have basically one side to associate with, right? So they get nervous and they're like, I really need you guys down below me to help out. It's kind of like that scene in Nemo where they were like, swim down, swim down. They really need the help from down below. So they're clinging on to dear life to be really tight and make sure nothing from the atmosphere, the air, the dust, whatever gets in there. So surface tension is all about intermolecular forces being stronger on the top, and this is the effect that allows water to bead up on your waxed car, even on your skin, or for insects to walk on it. Okay, I think you'll find this quiz to be really easy. I've combined the questions from lesson 15 and lesson 16 so that you can just review properties of liquids and solids at the same time. It's a lot of fact-based stuff. Not a lot of doing, not a lot of problem solving here. We are going to move on, and we're going to talk about properties of solids, and that comes from lesson 16. We're going to do all of the similar things. Okay, so we're just going to, again, revisit those intermolecular forces and how they pertain to kinetic energy. We're going to look at crystalline and amorphous solids. Again, not as in detail as I would have liked, as I did prepare but can't find. And then describe various types of chemical bonding that can exist as solids. So just reminding you here real quickly, because I know it's already fresh in your brain, solids have the most intermolecular forces between them. This table is made of strong intermolecular forces. This water, not so much. Even though it's hydrogen bonding, it's not as put together as the solid under my arm. And I can't break it. I can't even break it with applied force. So they're tight. They have very little kinetic energy. They are not moving. They don't heat up, cool down really easy. Water heats up, cools down really easy. The sunshine can do it. A little bit of heat in the room could do it. So finally, what we want to remember about solids is that the intermolecular forces far, far, far outweigh the kinetic energy. And when we have solids, we have several different types of solids. So you might have always thought to yourself, well, gee, is Jello a solid or a liquid? But it's a liquid. It's a liquid. For the most part, it's kind of one of those weird things. I think actually there's a technical term for it, but if we had to choose solid, liquid, gas, we would choose a liquid. It's kind of on its way to forming a solid, but it never does. Solids are in stark contrast to that. They really cannot be broken easily. You know, we take our finger, stick it in the Jello, and game over. But what we're looking at here is crystalline solids and amorphous solids. And you might think, well, that word amorphous kind of means a blob, right? So I think Jello's amorphous. But amorphous solids require something very specific, and we'll talk about that. Crystalline solids you're familiar with: sugar, salt, rock salt, rock candy, any kind of candy, probably for the most part, Jolly Ranchers, any kind of sucker candy. Solid molecules in crystalline structures are arranged according to crystal lattices. Okay, each one has their own, and it defines what that molecule or what that structure is. The crystal lattice structure for sodium chloride is different than that for sugar. It's made up of what we call regular unit cells, and the lesson goes in kind of deep detail about all this, and you don't need to know that. We're talking surface here. The fact that these unit cells, or what we've called formula units in the past, come together and continue coming together to build this much larger crystal. Clearly, there's not a lot of space between those atoms, nearly none, because they're held together so very tightly. So they're not compressible, and they do retain their shape. It takes a lot to reform a solid, or to break a solid, or to change the shape of a solid. So similarly, Play-Doh in its normal form would not exactly be a solid, because you can mold it and shape it, and you know, if you leave it out in the air and it kind of becomes like cement, then it's a solid. So and part of that's because Play-Doh has a high degree of water in it. So Play-Doh is a mixture to begin with. It's not a pure substance. For the most part here, we're talking about pure chemicals, pure substances. Okay, so within crystalline compounds, we're looking at diamonds, obviously the hardest substance, I think, known to man. Any other kind of gemstones, rocks, sugar, and salt, these are usually, the one defining feature, I think, of all of those is that usually you can see through them. Maybe not rocks, but sometimes, you know, the more like agates, if you go to a museum or something, you'll see these really pretty purples and blues and pink rocks, and you can see through slices of them. Sugar and salt, if you got under a microscope, you'd see they're clear and colorless. They're not exactly white. They look white because they're all mushed together. But diamonds and gemstones, all these things have regular cuts. They have shapes, and that's what defines them as being crystalline. Amorphous solids are very different from that. Amorphous solids lack that regular internal structure and actually end up keeping some fluid-like properties. That is, they can compress a little bit. They can mold and shape and move. They usually, a defining feature is that they can be melted and reformed. So we're not really talking about metals here. No, not metals, because metals fall into their own class of solids. But we do know that metals can be, you know, melted and formed into all sorts of different things, like horseshoes and our own jewelry, rings and earrings and necklaces. But really what we're talking about here generally is plastic. Oh, excuse me. Plastic makes everything under the sun these days, right? Makes up our computer. Some mold creates a plastic computer. This was a liquid. It solidified in a mold. My webcam, everything in front of me, really, wires, my glass cup with my spots on it. What else is plastic? My pen, my glasses, my lenses. I don't know. Everything is plastic, right? Glass. Similarly, you can have glass vases and glass cups. You can have glass, you know, the front of frames, the clear part of frames. Oh my goodness, sculptures. and little figurines. There's a whole profession actually that's called glass blowing. I think I could have taken it for 1 credit in college, but I didn't. You probably make some cool stuff in there. And rubber. Rubber like erasers, rubber like tires. Again, it can perform as a fluid until it undergoes some conditions like drying or something that would solidify it. Okay, taking a look real quickly just to look within that category of crystalline solids and the fact that they are determined by bonding type. We've talked about some of these types of bonding and not others. So ionic bonding you should be very familiar with, right? Ionic bonding is the plus minus combination of charges. We are usually dealing with nearly always metals and nonmetals. So I'm just going to make that note here. We have, in this situation, our metal plus the nonmetal, because one can form a negative charge and one can form a positive charge. Metal is positive, nonmetal is negative. We've also talked about the metallic substances, those seas of electrons. Sea of electrons, where basically all of the nuclei act as protons, and then all of your electrons are just sort of in a mesh around them, and they travel and move, and they're tied together in that way. We've also talked about covalent molecular. Covalent molecular substances are things like water. So they're bound with covalent bonds, but they have very defining intermolecular forces that kind of connect them all. Okay? And they become solids like water, for example. The one we haven't really dealt much with and is unique to this particular lesson is the covalent network. Covalent network atoms are strongly covalently bonded to one another, all atoms. Okay, so they're different from the covalent molecular type of solid or piece because these are discrete molecules connected by intermolecular forces. In a covalent network solid, you have discrete, similar or same atoms, all connected covalently or with covalent bonds, that is sharing electrons. Now, I showed it to you one time in the context of an example. We talked about a buckyball. A buckyball looks like a soccer ball. And I'm not going to be able to properly draw it here in 3 dimensions, but I'm going to try. That soccer ball usually has like pentagons, right? It's made up of pentagon. So if I kept going on and drawing that, this would be the buckyball, and it's all made of carbon. I think buckyball is formula C20, so they're all the same atom. They're all covalent bonded. We can also have carbon nanotubes, and I know I had you watch a video on those one time and how strong they are and how much promise they have for tomorrow's technology applications and building applications. Also in this category we have diamond, because diamond is nothing more than carbon. It used to be coal, right? Except it was subject to high pressures and high temperatures for like millions of years. So we have diamond. We also have something called graphite. Okay. Also all carbon. All of those are different carbon molecules connected in different configurations, all covalently. So that's really the only new thing there that we didn't know before. Take a look at the course and the lessons. They give you some really nice pictures on those. Again, I apologize for not including them. I had a few questions here for you too, but alas, they are lost. So, covering all our bases there with the goals, as I said, that is going to wrap up this entire unit. So yesterday in the recording, you watched and learned about phase diagrams. Today, we watch and learn about liquids and solids and how they're different from gases and what makes them what they are and what are some defining features about them. Tomorrow, and it is in the course right now, test review worksheet. Use your time tomorrow to complete and submit this worksheet. It will be worth points, probably 10, because it's long and it's detailed. The recording for tomorrow will basically be an answer key for this worksheet. So I'm not telling you that so that you don't complete it on your own and that you just come and you get the answers. I'm going to discuss through the answers what I can, but I really, really would encourage you to try it yourself first and then purposefully open the recording as an answer key. Check what you have, and if you don't have it correct, make the notes about why I said it is what it is. Okay? Because that lesson really can't be as interactive as I would like it to be. I'd be asking you a question every second. You know how those reviews go. So that's what to expect for tomorrow. And then we will just have you take the test on Thursday. See you back here again after the review on Friday for some details about your honors project. I haven't checked my K-mail yet today, and I think it's approaching 10 o'clock. I have so many more things to do. So chances are K-mail's not getting answered today, but I am going to keep on it. So keep sending me stuff if you have it. And thank you for, I popped on today to see what kind of activity there was in the lesson 14 video, and it looked like a lot of you worked through the entirety of it. I didn't see any votes at the end. I don't know if it gave you a survey or not, but if you're able to rate it, I would so appreciate your feedback because I'm interested. Now, this is the second one I'm making for you guys, and I realized from the first one I needed a little more energy, so hopefully I was able to do that for you, even though I'm so sleepy. Okay, see you guys tomorrow. Have a great one.